Frozen.
Hello.
Hi, Lex. How are you?
Very tired.
Tired? What'd you do over the weekend? Work?
Yeah.
Work on all your courses? It's almost over with.
Yes,
Almost
I'm
over
so excited.
with.
I'm so excited.
Yeah, I'll talk to you on the last day. Then you'll be excited, really excited. Okay, I think everybody's here. I think, well, there's Dion. She's coming in. So let's see what we got here. Yep, got everybody. Okay, let's look at, to begin with, what's coming up in the next week, which is really going to be the last week. I'm just going to be tying up loose ends for those additional few days at the end of next week. Well, in the end, I guess those first 3 days are quote class days, but we'll be just taking stock of what we've done and finishing up things. Let me show you the assignment sheet, and then I'll ask if you got any questions about anything else. Let's see. Okay, let's see what we got. All right, let's see if I can find the assignment sheet. Guys, when I look through all this is like half a semester here. I realize that we have done a lot, and I am well aware of that. Every one of these are things we've done, things we've looked at. There's a whole lot here, but let me show you where we're going. We're going to finish up Taylor series and McLaurin series today. I'm going to do some more examples for you and tell you what I want to do in terms of the, see, I got everybody now. What we want to do in terms of the homework and the few quizzes, because we're going to have one more test, and it will be predominantly on series, if not all on series. I've made a couple of things due, and then I'll fix you guys a sort of look. We'll look back at the kind of review sheet that I did, and maybe do some practice problems, getting ready for that test. The two tests I've got outstanding, I mean, the two quizzes I've got outstanding now are and some of you have given, I don't know, I hadn't looked at in my folder in the last day, I guess. Deborah, there was one I didn't have from you. Did you get it back? Did you get it to me eventually? Okay, good. I'll look for it. And I want to talk about that one today. But the other one is power series representations of functions, where you looked at something and said, well, it looks like a geometric series. I'm going to write it as if it were the sum of a geometric series. So I've got that one, and I'll take that one today, anytime today. You asked me questions about that on Friday, so I tried to answer what I could on that. Then this quiz is coming up on Taylor series and McLaurin series. This can be due Wednesday. I'm going to talk about it today, and then I'm going to let you loose with the homework and see if you have any issues with the homework. I'm going to do some more examples about that today. Does anybody have any questions about the power series when I got back to you? And Deborah, you're the only one I didn't get back, but the key is on Moodle. There were a couple of endpoints that you tested badly, and it was mainly a matter of sometimes simplification. So let me go to today's lecture, and I'll talk a little bit about that, and then go on and do what I was going to do today. Let's see if I can find that. Where is it? Taylor series. Yeah, there's the quiz. That's not it. Geez, did I lose it? It's not. Taylor series, McLaurin series. There's the quiz. It must be at the bottom. There we go. Okay. I introduced Taylor series on Friday, and I talked about it after I talked about McLaurin series. But the one thing I was going to say, and I'll just scroll up to try to do this right here. The one thing I was going to say on some of this, when you're using the ratio test, you get to a certain point and you take the limit, and then if that, you find out where that's less than 1 as the n goes to infinity. And then you'll have an interval, and then you test the endpoints. A lot of you, not a lot of you, but a couple of you, when you were testing endpoints, maybe you had something like this. I need to be careful with this. Number one, that this is not the right way to write that, unless you mean -1. I think what you mean and what you meant was that it was -1 to the nth, and that's very, very different. Okay, I yell at my algebra students all the time that -3 squared is not the same as -3 squared. This says it's going to alternate. This says it's nothing but -1. So you need to be careful with that. The other thing is when you're simplifying these things, for instance, if I had this, and I think this actually came up in one of those problems, it's the same thing as -1 to the 2n times -1 to the first. Notice you would add the powers here, but that's an even number. So this is always what? What's that always going to be, guys?
Even.
It's going to be even, and it's going to be an even power. And if I've got a -1 raised to an even power, that's just going to be 1. So, I mean, if you think about it like this, is you square it and then you raise it to the nth, then it's going to be 1 to the nth, which is 1. This one right here, then that's all that's left. And there was a minus there. And it's not alternating anymore. It's just a minus something. So I think on one of those you had to check. I can't remember if it was 1/3 or -1/3. Some of you thought it was alternating when it really was just the negative of the harmonic series. I think it was with that one. So take a good look at that and make sure you're simplifying things properly. I did put it on Moodle, so look at it, and I think you'll see maybe what your errors were. Okay, so questions about that. That's the last one I got back to you. And Deborah, I'll get yours back soon. Who's turned in the power series representation one yet? Has anybody turned that? Okay, Lexus, you turn that in. Anybody else turn it in?
That's the wrong one.
I'm talking about the one that had write a power series if you had something like this 2 over x plus 4 or something like that. That's the one I'm talking about. Okay. So look at that and make sure you get it to me. I think I said sometime tomorrow. Okay. And that's, so I'm backing it up a little bit, but I don't want to back this stuff up too much because I want you to get practice doing all the types of problems, and then you'll be hopefully ready for the test. Okay. Okay. So questions, anybody? Let me erase this, get this done. Let's do this. Clear page. It's a lot easier. There we go. Let's go back and kind of review what I did with Taylor series and Maclaurin series, and I'm going to sort of start it back here with a reminder of what these coefficients look like. If you've got a Maclaurin series, let me move it up a little bit. If you've got a Maclaurin series, and remember why we said we were doing this? We were doing this by saying, well, what if it doesn't look like a geometric series? This will work for writing any series any function as a series. If you've got a Maclaurin series and you've got something that looks like this, you want a series representation that looks like n equal 1 or n equals 0, I guess, to infinity of a n x to the n. That's a Maclaurin series because it's about 0. Okay, and if you were to write out terms of that, it would look like this: a0 plus a1x plus a2x squared plus a3x cubed, and so on and so forth. And what we found out on Friday was that these coefficients look like this. A sub n looks like fn of 0 over n factorial. Okay, so that you'll know what every one of these things look like if you will just plug it into the function or its derivatives. Okay, so Deborah, I'm getting some, is there somebody talking behind you? I put your mic on for, I mean, put your mic, cut your mic off for a second. Yeah, okay. If you need to, turn it back on if you need to ask me a question. That's what that looks like. If you're doing a Taylor series, it looks virtually the same, except you find the coefficients like this. ANs are equal to the derivatives evaluated at C over n factorial. And if it's a Maclaurin series, it's going to have x to the nth powers in it. If it's a Taylor series, it's going to have x minus c to the nth in it. Okay. All right. I want to go through completely go through a couple of examples here. And I think I'll do a Taylor series first. And then maybe I'll do, you know what? I think I'll do a Maclaurin on this one and a Taylor series. So I'm going to try Maclaurin first, so you can see the difference. So what I'm after, this is the function f of x equal 2 to the minus x, okay? And I would like to write some sort of series representation for it. Now, if I were writing a Taylor series, it would look like the sum from equals 0 to infinity, n equals 0 to infinity of an x minus 2 to the nth. The 2 comes from here. I know with a Taylor series, I'm looking at powers of x minus 2. And so what in general it would look like, if I wrote out some terms, it would look like that. Your job is to find out what the A0, A1, A2, A3, and so on are, and then try to look at the pattern and write it as a series. So let's do the Taylor series first, and then we'll come back and do the Maclaurin series. Okay, so here's what I need. I like to look at the function first and find some derivatives, because after all, that's how you're going to get these ANs, by looking at and if n is 0, that just means the original function. If n is 1, that's the first derivative. If n is 2, that's the second derivative, and so on. So I'm going to find myself some derivatives of the function. Okay, so f of x is 2 to the minus x. F prime of x. What's f prime of x, guys? Help me out with this one. Maybe we hadn't differentiated this one in a while. What does it look like?
Natural log.
Okay, good. Got a natural log of 2. What else does it do?
Divide by.
You're thinking about the integral, Alexis, I think. Do the derivative. What it does is it has a natural log of 2 of the base, and then it repeats itself, sort of like e. Remember that one? Okay.
2.
So it's natural log of 2. It repeats itself, and then multiplies by the derivative of the power. Okay? So it looks like the exponential function, except it's got this log 2 down there. As a matter of fact, if this were e, the natural log of e would be 1, so you wouldn't see that. Okay. So that's what it looks like. So next thing I'm going to do is say, okay, let's look at what that is. I'm going to write a little nicer. Minus natural log of 2 times 2 to the minus x. And we are doing a Taylor series around 2. So I know I'm going to have to find f prime of 2. Right? And for that matter, here I'm going to have to find f of 2. By the way, what is f of 2, guys? It's 2 to the negative 2. So I'm just plugging it in there. So that says A0, put a 0 in here. A0, the first thing on this series, will be whatever that function is evaluated at C, which in this case is 2. So it'll be 2 to the minus 2. 2 to the minus 2 over 0 factorial, which is just 1/4. So we'll look at that. Okay. So that's my A sub 0. Now, let's look at what f prime of 2 is. If you look at what f prime of 2 is, you wind up, you have this minus natural log 2. And then you plug in here, you'll have 2 to the minus 2 again. All right, let me fix that. So you'll have 2, you'll have 2, can't get it right, 2 to the minus 2. And that would be the natural log of 2 over 4. That means that A1 is going to be that thing right there minus the natural log of 2 over 4 divided by 1 factorial. So I took the derivative, first derivative in this case, and I wrote the A1 is going to look like that. Okay, it's over 1 factorial. Okay, what's your question?
Why is the natural log negative but the 2's not?
What 2? Which 2?
Like, is it
This one?
I guess, yeah, that one.
Okay, because when I wrote it out, it was 2 to the minus 2, Alexis, and I dropped it down into the denominator. That's how I got that 1/4. 2 to the minus 2 is 1 over 2 squared, right?
I don't know.
No, yeah, you do. Negative powers. Tell me this.
I think I'm just confused because like only one piece of it's negative, another part's not.
Yeah, that's the only negative sign right there. This is a negative sign, but it's a negative power. What do you get when you raise 2 to the negative 3? Forget about what I just did. What do you get when you raise 2 to the negative 3?
Negative 8.
It's not negative 8. What happens when you have a negative power? Where does it drop?
Oh, to the bottom.
To the bottom. So that would actually be 1/8, wouldn't it?
Oh, yeah. Okay.
That's what I did with this. I dropped it to the bottom. I didn't want to look at that negative power, so I'll just write 1 over 2 squared. That's what that is right there. Okay? I'm going to do it again, but you see what I did there?
Yeah.
Okay. So this looks a little funky, but I'm going to go with it for a while and see what happens. All right, the next thing I'm going to do is find the second derivative. I only do about 3 of these, and so maybe we can get the pattern of it. Well, there's the first derivative. So I'm going to take the second derivative. Minus log 2 is just a constant, so I'm just going to write it down. Now, what's the derivative of 2 to the minus x? Well, it repeats itself. 2 to the minus x times the minus 1 times the natural log of 2. All right, so again, that's just a constant. I did this from the first derivative. That's a constant, and then the derivative of this is the same as it was before. It repeats itself, multiplies by natural log 2, and then the derivative of minus x is minus 1. Let me clean it up a little bit. Minus a minus here is actually going to give me a plus log 2. 2 to the minus x, and then how many log 2's do I have here, guys? Look at it. How many log 2's do I have?
2.
I have 2 of them, so I'm going to write this as log 2 squared. Now I'm looking for a pattern, so I'm only going to go so far here.
Yes.
Question.
Yes. Like, where are these numbers coming from? Like,
These numbers are coming from the derivative of 2 to the minus x. I'm just differentiating things over and over again. I could have asked you to do this way back in chapter 8 when we learned how to differentiate an exponential. So look at it again. What's the derivative of 2 to the minus x? It's log 2, 2 to the minus x times minus 1. I cleaned it up. Then I'll worry about plugging the 2 in a minute. Let's look at the next derivative. And then I'm going to look at the next one. But what's the derivative of that? Well, that's just a constant. So I just wrote it down like it was a 5 or something. What's the derivative of 2 to the minus x? It's 2 to the minus x, log 2 times a minus 1. When I clean it up, I get log 2, I get 2 of the log 2's. Minus a minus is a plus. Because the one before it was minus, and then I had to multiply again by the derivative of minus x, and I still got a 2 to the minus x. All right, I'm going to go back to that. I'm going to do one more derivative. Maybe I'll do 2 more derivatives. So I'm going to go back, and I'll plug the rest of the stuff in a second. I'm going to get rid of this page. I'm going to get rid of this thing right here. So, because I'm going to need room to write here. Come on. Come on. All right, you won't let me erase. I'll erase you myself. Okay. All right, I'm gonna do a couple more words. Then I'm gonna write it and see if we can see a pattern. Oh, give me this. I feel like a kindergartner. Messed up their picture. And I should be able to clear the page, but come on. Ah, there it is. Shit. Sorry. Clear the page. Okay. Now, I'm going to go back. All right, I'm going to find the third derivative. Watch carefully. And I'm just doing more and more derivatives here. But you know what? That's just a constant. So I'm just going to write it down. Natural log of 2 squared. Now, what's the derivative of 2 to the minus x? Same as it always was. 2 to the minus x log 2 times minus 1. How many logs do I have now? How many logs do I have now, guys? If I want to simplify this, how many logs do I have? 3. Okay, Deborah's waving at me. She's got 3 because she's got her mic off, and I told her to take her mic off, but I got 3. So that's log 2 cubed. 2 to the minus x is still there, and this time there's a minus. I'm going to do one more. Then I'm going to start looking for my series. So the fourth derivative here, that's just a constant. Now, what's the derivative of 2 to the minus x? Same thing it always was. 2 to the minus x minus log 2 and a minus 1. Simplifying it, minus a minus is a plus, and now I got 4 logs and a 2 to the minus x. Now, I'm gonna see if you can, I want to see if you can predict for me what the fifth derivative is gonna be. Because I think we got enough to go on in terms of a pattern. What, is this thing alternating or not?
Yes.
Yep, it's definitely alternating. We started out with the function just being 2 to the minus x, and then f prime was minus. F double prime was plus. F triple prime was minus. The fourth derivative was plus. What do you think about the fifth derivative here, guys? I'll look at the fifth derivative. What do you think about that?
Minus.
It's going to be, yeah, it's going to be minus because that other one was plus, so this is going to be minus. How many log 2s do you think I'm going to have?
5.
5. Good. Does everybody see where Tara's getting the pattern? Here's what I'm looking at. Fourth derivative, 4 logs. Happening every time. All right, and I should have put a parentheses around that. And then we always have the 2 to the minus x, and that's it. Okay, I see the pattern. The sixth derivative is going to be positive. That's going to be the 6th power, and there's going to be another 2 to the minus x. Now, here's what I need to do. I'm going to go back up a little bit, and I'm going to say that I had already found, let me put these in blue to make it look a little better. I had already said that these coefficients are going to look like this. They're going to look like an is the nth derivative with the c plugged into it over n factorial. So what I did with a0, that was the function. There was no derivative to it, so I just plugged in 2. That was 2 to the minus 2. I got 1/4. When I wanted a1, I'm going to plug 2 into it. It'll be minus log 2. It'll still be 2 to the minus 2, which is over 4, and that's 1 factorial. All right, now I want you to, so there's the first 2 of these things. Let's look at the next one. A2 is going to be the second derivative with 2 plugged into it. All right, all over 2 factorial. Now let's see what the second derivative with 2 plugged into it is. It's going to be, let me scroll up a little bit. It's going to be log 2 squared. Log 2 squared. And then 2 to the minus 2. But you know what? What's 2 to the minus 2? Anybody?
1/4.
1/4. Now, be careful because this one is over 2 factorial. So it's going down there. That 1/4 is going down there with a 2 factorial. And I'm just going to leave it like that. And again, because I'm trying to look for pattern. Okay, so the 1/4 came from this. I just rewrote it as a 1/4 in the bottom. And if it's if it's A2, it's over 2 factorial. All right, I'm going to do the next one. This would work way better on a long blackboard, but now I got this long vertical thing. But I will get the pattern going when I put them down next to each other, okay? All right, let's look at this one. A3 is going to be the third derivative evaluated at 2 over 3 factorial. I've got minus log 2 cubed from that, and then 2 to the minus 2 all over 3 factorial. Now, what's going to happen to the 2 to the minus 2, guys? Minus in that. What's going to happen to that thing?
1/4.
4 in the bottom. End up being 4 in the bottom. Now, I think you can see the pattern. I'm going to do maybe 1 or 2 more. A4 is going to be the 4th derivative evaluated at 2. And that's going to be over 4 factorial. The 4th derivative is right here. That means I'm going to have a log 2 to the 4th. And then I'm going to get 2 to the minus 2, which we already know is going to drop down as a 4 and to go down there with my 4 factorial. Finally, a 5th, and then I'll start looking for my pattern. I think you can see what the pattern is, but if I go to the 5th derivative with 2 plugged into it over 5 factorial, the derivative and the factorial always match up, guys. And along with the thing you're trying to find. A5, 5th derivative, 5 factorial. If I plug the 2 into this one, it's going to be minus natural log of 2 to the 5th. 2 to the minus 2 over the 5 factorial. But guess what? 2 to the minus 2 is over 4. All right, now I want to write out what I've got here, guys. I'm going to have to look at it. You guys might want to tell me what some of the terms are, but let's see. The first term was 1/4. So my series, whatever it is, by terms of my series, for 2 to the minus x about 2, the first one, the A0, and we'll go back up here, was just the function evaluated at the point over 0 factorial, which is 1/4. So that's what I'm going to get right there. The next one, and by the way, that's the 0th derivative. I'm going to put this here so you'll sort of can keep track. That's like x minus 2 to the 0th power. But x, because it's going to be in powers of x minus 2, but I'll put that there so we can see the pattern. The next one, we'll go back to A1. It's minus log 2 over 4 over 1 factorial. Minus, where'd it go? Oh, okay. Hang on. There we go. It's going to be minus log 2. It was also over a 4. That was 0 factorial. This is 1 factorial. And again, I'm going to leave it down there because I need a pattern in the end. And that'll be x minus 2 to the first power. So there is your a sub 0, x minus 2 to the 0. There's your A1 right there. Your next one's going to be your A2. So if I go back and get my A2, it's log 2 squared over 4 over 2 factorial. And it's a plus. log 2 squared. There's a 4 down there, and there's a 2 factorial, and this will be x minus 2 squared. All right, I'm going to write a few more. I think I got the pattern now, though. You know what? I think the next one, if the next one I had plus, minus, plus, the next one's going to be what? What's the next one? It's going to be minus. And we know it's the A3. So it was going to be log 2 cubed, x minus 2 to the 3rd power. It was also going to have a 4 down there, and it was going to have a 3 factorial. Finally, I'm done after this. Well, I'm not done. I want to look at the pattern. I want to rewrite it. The next one will be positive. A4 is log 2 to the 4th power, x minus 2 to the 4th power, and this thing ended up, there was a 4 down here again, and this was 4 factorial. Now, plus, dot, dot, dot. I want to write what this looks like in series notation. So here's what I'm going to do. I'm going to use the pattern. And when I say write it as a series, that's why you've got some terms here, but we can see a pattern. If this goes from n equals 0 to infinity, number one, I know it's alternating. So what should I put in there if it's alternating?
-1 to
You got it.
n.
-1 to n. Yeah. And you can check it. For instance, if I let n be 0, the first term would be positive because it would be -1 to the 0. If I let n equal 1, the second term, the A1 would be negative and so on. So that gets me my alternating in there. Now, what about, let's work on the logs next. You don't see a log in this one because you know what, guys? It really was natural log of 2 to the 0th power, and that's going to be what? That's just going to be 1, right? So what's going to go in here for that? A1 had the 1st power, A2 had the 2nd power, A3 had the 3rd power, A4 had the 4th power. What's going to go in there, guys?
N.
N. Yep. Log 2 to the nth. Now, let's look at, and of course, the power x minus 2 to the nth, because that was always 0, 1, 2, 3, 4. That's what your series is counting to. What was always in the bottom? There was one thing that was always in the bottom of these, and what was it?
N factorial.
There was an n factorial, and there was something else that was always there.
A
Not
4.
4.
Exactly. And guys, that's not 4n factorial. That's just 4 times n factorial, okay? 4n factorial is totally different than 4 times n factorial. But that gets me the series. That gets me the series right there. It's alternating. You know, if you wanted to find out what the interval of convergence was, you'd use a ratio test on it, okay? You'd use a ratio test on it. And lots of stuff would drop out. Why don't we do that? Let's just do that. And then I'll do Maclaurin series with this one and you'll see the difference. Is everybody, you gotta do the individual terms according to that thing that said A sub n is the nth derivative evaluated at C over n factorial. And you gotta do that for whatever function you've got. You know, we did it for sine and cosine. We did it for sine. Maybe if I have time, I'll look at another one of those, but you're just evaluating the function at a point. That's how we got all those log 2s in there, all right, and how we got the 1/4, because it ended up being 2 to the minus 2 every time. Let's see where that converges. Then I'll do the Maclaurin series. That thing's going to converge. Okay, so we're looking at the convergence. The limit as n goes to infinity, put the absolute value on here. See what I get. That's going to go on top. I mean, no, if I got to plug in what to go on top there, guys? You tell me. What have I got to plug in?
N plus 1.
Yep, I got to plug in the n plus 1. So I'm going to get -1 to the n plus 1, log 2 to the n plus 1, x minus 2 to the n plus 1 over 4 times n plus 1 factorial. And guys, allow me to shortcut this. Then I'm just gonna, I would divide by this thing, so I'm just gonna invert it. I'm just gonna go ahead and invert it. Let me get rid of this. Okay? Well, that didn't help me much. Didn't help me at all. All right, I'll go ahead and invert this thing. So what's gonna go on the top is 4n factorial. And what's gonna go on the bottom is minus 1 to the nth, log 2 to the nth, and x minus 2 to the nth. I get it all? There's 4n factorial minus 1 log 1. Okay, that's great. I got it all. All right, let's simplify that. That's going to be the limit as n goes to infinity. Basically, you guys were doing the ratio test right. I just want to see what happens with this one. Let me move this over here. How about the minus 1s? Minus 1 to the n plus 1 or minus 1 to the n will just leave me with minus 1, and the absolute value of minus 1 is just 1. So I don't have to worry too much about that one. How about log 2 n plus 1 over log 2? Let's change the color of my pen. How about this, combining this one and this one? So that one's gone, basically. What's that going to be?
Natural log of 2 in the numerator.
Yep. Natural log of 2 to the first, because I got n here and n plus 1 there. The 4 is going to go, so it's gone. How about x minus 2 to the n plus 1 over x minus 2 to the n?
You're left with 1 in the top.
All right, I'm left with 1 in the top. How about n factorial over n plus 1 factorial?
You're left with n plus 1 in the denominator.
Good. N plus 1 in the denominator, and that's it. And remember that I'm letting n go to infinity, so basically I can take out this log 2 and leave that at x minus 2 in there. Log 2 is positive, so the absolute value is going to be that. What about the limit as n goes to infinity of 1 over n plus 1?
0.
Yeah, goes to 0. So that thing right there is going to 0. That means it doesn't matter what in the heck this stuff is. Anything times 0 is going to be 0 for any value of x. So it's 0. What does that say? If that comes out, if your test comes out like that, what does it say?
For all x.
0 is always less than 1, so that thing converges for all x. Here's all of, let me get rid of that. Okay, so converges for all x. So this thing converges for all x. Okay, so so it's convergent for all things. I can estimate something very close. I mean, in this series. All right, I'm gonna do Maclaurin series, and you know, you're saying, oh my God, do I have to go through this again? Turns out that Maclaurin series is a lot easier, because Maclaurin series you get to plug 0 into your derivative, and that makes things nicer. So I'm gonna do the Maclaurin series and see if we can come up with a pattern for that. Remember that the Maclaurin series is going to be in powers of x, because it's x minus 0. Remember that an always looks like the nth derivative, and for Maclaurin series, we're not going to plug in c, we're going to plug in 0. That's nice. I'm going to plug in 0, it'll still be over n factorial. So let's see what we started with. F of x was 2 to the minus x. So that means f of 0 is going to be 2 to the 0, which is just going to be 1. That's good. So that means a0 is 1 over 0 factorial, which we know is 1. F prime of x look like 2 to the minus x times log 2 times minus 1. That's 1 right there. So A1 is going to look like plug in 0 to this thing. You'll just get minus natural log 2 plus 2 to the 0 is going to be 1 over 1 factorial. Second derivative. I think we remember what the pattern was, guys. We ended up with 2 logs. It was positive and a 2 to the minus x. Nice thing about this, I get the plug in 0. Oh wait, there was one other thing in it though. What was the other thing in it? In this one, there was a 1/4 in it, wasn't there? Let me look back at the derivative. Oh, you know what? There's not going to be a 1/4 in here because that was because I was plugging 2 in, and that's 2 to the minus 2 was 1/4. Now I'm plugging in 0 in, so all I get is 2 to the 0. So that's log 2 squared. 2 to the 0 is just 1. That'll be over 2 factorial. Now look so far. Let's do a couple more, and then I think we can see the pattern. F triple prime of x. F triple prime of x look like a negative. Notice if the derivative was odd, it was negative. Cubed 2 to the minus x. All right, if I evaluate that, that's going to be at 0. It'll be minus natural log 2 to the 3rd power over 3 factorial. Finally, I think I can get a hold on it now. Next one is going to be positive. Log 2 to the 4th, 2 to the minus x. Okay, A4 then, 2 to the 0. This thing evaluated at 0. It's just going to be log 2 to the 4th over 4 factorial. Now, let's write the Maclaurin series. Let me see if I can pick them up easily here, and then we'll call it a day. A0 was 1. The next one was minus log 2. The next one was log 2 squared over 2 factorial, and then minus log 2 over 3 factorial, and then that. So here's what it looks like. This series, which I'll figure out the pattern for it in a second, n equals 0 to infinity of whatever. A0 was, I forgot, 1. A0 was 1, and that'll be x to the 0 power. The next one was minus log 2. Minus log 2 over 1 factorial, and that'll be x to the 1st power. The next one was log 2 squared over 2 factorial x squared. Next one was minus, let's see, plus, minus, plus, yeah, next one's gonna be minus. Log 3 squared over 3 factorial times x cubed. Now, I want you to tell me what the pattern is, guys, because it's not that hard. What's this thing over? It alternates, so we really still need that in there. What's in every other one of them? What's in every one of them then, guys? We got this log 2, and it gets raised to a higher and higher power. So log 2 to the nth. This was powers of n over what? This was a 3, right? It's over n factorial, right? Okay. Put in 0. You get powers of 0 here. You get 1. So it's just 1. Put in 1, you get a minus, you get a log 2, you get x to the 1st over 1 factorial. There it is right there. Now, the things you have to be careful with. I didn't give you a whole lot of these things to do, and sometimes they only ask for 3 terms. So you do as many terms as they ask you. make sure your derivatives are right. So for example, they might ask you to do one for f of x equals sine x, where you're going around pi over 2. So you got to find all your derivatives. You got to plug pi over 2 into them. Then you got to put them over the factorials, and then you'll be ready to do it. I think I did give you one that's a little harder, and it was a tangent. I got to find my derivatives. What's the first derivative of tangent, guys? Secant squared. Now, I don't know how many derivatives I'm going to have to find, but notice that's like secant of x squared. If I wanted to find a third derivative, a second derivative, I'd have to use the chain rule. I'd have to bring the 2 secant x to the first down here times the derivative of secant, which was secant tangent. And you can see that this one's going to get nasty fast. If I multiply the secants together, I'd have a tangent. Now, if I ask you to find the third derivative, what would you have to use on that?
I mean, the product.
The product rule, exactly. And it just gets uglier and uglier. I think when they did, I did put this one in, and I think they said find only 3 terms. So you gotta be careful with your derivatives. Okay, please work on the power series representation thing if you hadn't finished. This one is not due until, when did I have it due? I can't even remember anymore. Wednesday or Thursday. Get this done. This is the last thing we're going to do with series. Tomorrow, bring your calculators. We're going to start playing with polar coordinates. And that's the first thing we're going to do. We're just going to play with a bunch of graphs. Okay. Tiara, is that a smile or a question, anybody?
Yes. So I'm confused.
Okay.
We did the Taylor series. That's because it was C equals 2.
0. Yeah. With the Taylor, no, C was 2 in a Maclaurin series is a special Taylor series where you let C be 0. Everything else is a Taylor series.
Okay, so that's why we had to plug in 2s for the other one.
Yes, because it was in powers of x minus 2. This is in powers of x minus 0. A Maclaurin series is always about 0. A Taylor series is about something other than 0.
So I'm confused. Why didn't we just use the Maclaurin one first then?
Because what the Maclaurin does is find good representations close to 0. So if you wanted to estimate something, this would be good for things close to 0. Remember that other one was centered at 2? If you wanted to find something that was close to things that were closer to 2 than 0, you'd use the one with 2.
Oh, so we were just trying to see.
Yeah, I was just picking a C. I was just picking one. I could have picked 1. You know.
Okay. So there is a different C other than 0 we used.
Yeah, it's a Taylor series if I use something other than 0. It's called a Maclaurin series if I use 0. You can see it's messy. You've got to keep yourself organized in terms of the derivatives and then what you plug in when you get them and then what your coefficients are. Okay. Any other questions? So it did take me a while to do those 2 problems. So there's not a whole lot of homework there, but make sure you get through at least 2 or 3 of them, okay?
Is due tomorrow or Wednesday? Thursday?
I think it's due Wednesday. I think I put it on Wednesday.
Okay.
Try 1 or 2 guys tonight so that you can see if you're doing the right thing. You know, you don't have to do 1,000,000 of these things to understand if you got it. You just got to be careful with your derivatives. Are we good?
Yeah.
Who knows? Okay. 1 more day down. 1 more day down. I know you were going to miss me, so I've decided that we're going to hold classes till the end of May. No, not funny. Okay, whatever. I promise I'll end. Are y'all having new material in most of your other classes next week? Or is in chemistry and stuff like that?
Yeah.
Okay.
Like
yeah.
1 more chapter.
Okay, I'm going to end this I'm going to end the material at the end of this week and then just take whatever time I need to do to tie up loose ends before we take this last test. Okay. All right. Any questions? Thumbs up, maybe. All right. Okay. I'll see you tomorrow. Okay. Bye.